All right, so this is work with Zehui Zhao and Rohan Mehta, who is here. And the question is, look in your genome. What is the time to the most recent genetic common ancestor? What do I mean by that? Let's imagine scanning along your genes, let's say in one chromosome. And asking, when were your two copies? When do they share a common ancestor? And because we're sexual, you'll have one answer for one gene, and then another gene will have a different answer. Another gene will have a different answer. Another gene will have a different answer, etc. And what we want to know is, what's the most recent? This is the most recent for each gene. What's this time? The one that was the most recent time. Okay. So yeah, most recent squared. Okay, so why might you care about this? It's used in some demographic inference models. IICRK uses it. MSMC2 uses it. There's some simplification. It's kind of a simple quantity to calculate in some sense, I'll argue, which I suspect is why they use it. But for me, what happened is Stefan Schiffels, the developer of MSMC2, asked it on social media, and I was just completely nerd sniped. Like, you know, that's such a simple question, simple model. We should be able to answer that, right? And hopefully with this audience, some of you feel the same way. You just want to know the answer to this thing. Okay, so what would be like a really naive answer to this problem? You could ask almost the same thing. You could just say, when's the first common ancestor of your mother and your father? Okay. That is very recent. Every generation you go back, they have doubled the number of ancestors until they share an ancestor. And that happens in only a logarithmic amount of time in the total population size. After that time, everybody in the population back then was an ancestor. Okay, but as discussed in Nick Barton's section, that is not relevant to our question, because most of those ancestors, because there's so many of them, are not genetic ancestors. Most of your old ancestors, you got no genes from. So who cares if they're shared? It's not showing up in the genome. So really, this is just a lower bound. You can't have shared a genetic common ancestor if you didn't share a genealogical common ancestor, but it's going to actually be much longer than that. Okay, and so just like if we're thinking of kind of like a humanoid population where we just say, oh, I'm going to treat n as about 10 to the fourth, our intuition here is that this would be kind of, order 10-ish generations. So very, very short time. Okay, what's the other kind of extreme that you could take? It's the one that that John talked about. You could say, what about a typical gene? Right? So if you just look in the genome and pick a random gene, the time to a common ancestor is going to be about n generations. Okay, so here, if we don't go to infinity, but we stick with, say, 10 to the fourth, all right, we have a time of order 10 to the fourth. Okay, now, but this is a typical gene. We're asking about the first gene to coalesce, so it's definitely going to be faster than this. So this is kind of an upper bound. Or it is an upper bound. It has to be faster than this. And we see we have quite a bit of space between our lower bound and our upper bound. Right? So we're somewhere in there. Okay, what haven't I used it all yet is oh, sorry.
Just quick clarification. N is the number of people you're looking at?
Yeah. So this time, let's say T genealogical.
The effective number of people.
Oh my God, yeah, whatever. Humanoids, not real humans.
Number of effective people.
Yeah. It gets a little, I mean, maybe this is a different number, but yeah, let's say effective. Yeah. Coalescent number, yeah. Okay, so we're somewhere in between these, you know, and 10 to the fourth is not that many, right? We could easily have 10 to the sixth, even bigger in a natural population. So there's quite a, orders of magnitude range between these two. So we're somewhere in there. Where should we be? What we haven't used it all yet is the actual recombination, right? The fact that we have this recombination splitting up the different ancestry. So what is recombination going to do? If we imagine tracing the ancestry back in time from the present to the past, and we say here we've got kind of, here we've got your maternal chromosome, here your paternal. As we go back in time and trace the ancestry, these are going to split up due to recombination.
Actually, slides are still being shared, which is making things look terrible.
Oh, my bad. There we go. Okay, sorry. There we go. All right. Yes, I can. Okay, good. Okay. Okay, sorry. So there's as we go back in time, the lens is split. Let me say that these are not necessarily. Yeah, let's say these are regions of chromosomes, and so I'm not. We can. Let's make this guy go up further and then split here. Okay. Let's say that we work in coalescent time, which John introduced. I'm going to call that tau. He used it for something else, which is the number of generations divided by the typical coalescence time. So over here, what is a typical unscaled coalescence time of n is a typical scaled coalescence time of 1. Okay, so we're measuring it in the natural units of coalescence time. And let's say this has map length r. It'll have a scaled map length rho equals nr. And these splits are going to happen at rate rho. So if we go back a long time, there'll be a bunch of lineages about rho tau of them per sample. So there'll be rho tau of your paternal ancestors, genetic ancestors, rho tau of your maternal genetic ancestors. Okay, so now the question is, what is the coalescence rate caused by these by all these lineages? Okay. Now, naively, you'd say all of these guys can coalesce with all of these guys. So I square this, and that's my number of coalescent events, possible coalescent events. That's my rate at which they'll start coalescing. That's true, but we're kind of back in this problem. If this lineage, who's ancestral to say like the first leftmost gene from your maternal chromosome, coalesces with this lineage, which is like the rightmost gene from your paternal chromosome, it's not a genetic common ancestor because it's two different genes. It's not an actual shared ancestor between the genes. So instead, we need to think about what's happening at the level of the genes. What is the coalescence rate in these different states? Okay, so let's over here. If we look early on, here's chromosome 1. Here's chromosome 2. There's only one lineage. There's only one lineage per ancestor or per parent. We have two lineages, and our coalescence rate is unity. Okay, now here we've split one of the lineages in half, and the other one is still whole. Okay, now how many pairs can coalesce and actually create a genetic common ancestor? One here, one here. That corresponds to this guy coalescing here or this guy coalescing here. So we have three lineages here, 1, 2, 3, and we have two possible coalescent pairs. All right, now let's go up here. We still have that first split, and now we've added a second split in the other ancestry. And now what? We have one there. That's a possible genetic common ancestor. That's a possible genetic common ancestor. And that's a possible genetic common ancestor. So when we have 1, 2, 3, 4 lineages, we have 3 pairs that can coalesce. And importantly, this guy coalescing with this guy does us no good. That's not a genetic common ancestor. Okay? So now we see that if the number of lineages is k, the coalescence rate is k minus 1 QED. So now we can actually answer it. It's not squared in the number of lineages. It's just linear. So we see that the coalescence rate at time tau is about 2 rho tau. There were rho tau lineages per sample, 2 samples, 2 rho tau total lineages. That's our coalescence rate. Okay, so what does that mean? Our coalescence rate is not constant anymore. So if we look at our CDF, this is our single gene CDF. Instead, when tau is small, it's going to start off very low. We have a very low rate. And then it's going to shoot up. And then we're going to be almost certain to coalesce. In other words, if we look at the PDF, what we're going to have is instead of it being high at low times, it's going to be low. Or rather, it'll be proportionally low. And then it will spike up hugely and then crash down. We want to do this a little bit more mathematically. What would we say? We'd say the probability that the most recent common ancestor is greater than tau, would be about e to the minus the integral of this, rho tau squared. That's 1 minus that CDF there. So that's what I've just plotted. And you differentiate this to get the PDF. So what do we see? What's kind of the typical value here, the typical scale, where this is kind of starting to decay? It's about 1 over the square root of rho. That's where this exponent is order 1. When tau is much smaller than that, we definitely don't have a common ancestor. When tau is much greater than that, we've definitely already had the common ancestor. In unscaled time, we have to multiply by n. And recall this is nr. So in regular generations, the time is square root of n over r. Very funky scaling. Okay, so let's put that on here. We're kind of saying for any gene, typical time is n. For the first gene, it's square root of n over r.
What exactly is R?
Oh, sorry. R is the length of our, yeah, no, sorry. Thank you for reminding me. Yeah, it's the length of our sample genomic region. So let's say it is a chromosome in people. So then this might be order 1 in unscaled units. Okay, so for our humanoids here, if we take the square root of 10,000 over 1, this would be order 100 generations. Okay, so it's in between, it had to be, the 10 for the genealogical common ancestor and the 10 to the 4th for the typical gene. And you can see like the genealogical common ancestor was log n scaling. The typical gene has linear n scaling. And the square root of n is kind of like halfway in between those on a geometric scale. So that's kind of I don't know if it had to be that way, but it's a kind of a nice coincidence. But it's a very weird scale. I'm not used to seeing this kind of square root scaling of n in a coalescence time. I'm also not used to seeing this kind of square root scaling of r showing up in something. So the kind of the weirdnesses are playing together to give them something sensible. You can straightforwardly extend this. If instead of talking about 2 samples, one person, 2 haploid samples, you want to do everybody in the room, you can take it to any n you want, any sample size you want, not just little n equals 2. And whereas for this single gene, this time would go down quadratically in n. For this problem, it actually ends up going down only linearly for somewhat similar reasons. Well, vaguely similar reasons to what we saw over here, where this was not quadratic, but it was linear. That's it.
Question.
Noah had his hand up.
Yeah, so I mean, this seems like the kind of problem where maybe one wants to do a simulation to kind of see whether it matches and what the distribution looks like in a simulation, and that's maybe not a trivial simulation to do. I'm just curious if you've kind of thought about that as part of this, because I mean, like, it is sort of a naive view of this same question. It's like you've got coalescence time n in each location, and maybe you have some model of how many different fragments there are of the genome with distinct coalescence times in your process. over there on the left, and then, I mean, it's kind of a totally different way of thinking about this, but leads to kind of like a linear solution with something like substantially less than n, but like a small multiple of n, rather than an n scaling. And I mean, I think that there's you know, maybe I kind of, you would like to see kind of how the approximations all play out, like when it's simulated.
Yeah. So okay. So simultaneously to me getting nerd type by Stefan, Peter Ralph did too. And so, you know, he did. It was like 1 minute for me to do the quick and dirty version of this, and 1 minute for Peter to write the MS Prime simulations and run them. He's a beast, and they do match. Zehui did it like much better. He did like the real theory with the generating functions. If anyone was at Lindy Wall's talk, and it got the actual answers for this, and did like the real careful simulations, and they do match very well. But the basic picture is still this.